While you're getting out your notes, we're going to watch a little video here.
Is that music one?
Yep.
Yes. Great. I love
Acids and bases, in life you have a place. Acids have a hydrogen, hydroxide for a base. Acids give off H plus when in water they are stirred, forming H3O plus. Hydronium's the word. The more hydroniums there are, the lower pH gets. All because the silly acid had to go get wet. Reactive metals like Ca and Fe oxidize. When reacted with an acid, they can really shrink in size. Gaseous hydrogen is formed, as well as salt and fat. But metals like AU, Ag, and Cu won't react. Acids and bases, in life you have a place. Acids have a hydrogen, hydroxide for a base. Bases yield hydroxide, OH minus how we write. When dissolved in water and disappear from sight, the more hydroxide ions, the higher pH slopes. The more slippery it feels as it turns your skin into soap. Fats are hydrolyzed by bases, turns them into soap, which can be fashioned into bars or dangled from a rope. Bases form when active metals, H2O, are placed. Sodium forms sodium hydroxide, a strong base. Acids and bases, in life you have a place. Acids have a hydrogen, hydroxide for a base. Put the two together and you get some real neat stuff. It's called neutralization. I can never get enough. It makes water molecules and salt with no regrets. Titration's what you call it when you mix them with purettes. Ava equals mub can be used to calculate concentrations of an acid or a base when you titrate. Just remember that Ma or Mub will get multiplied by the number of each ion by which they're identified. Acids and bases bases. In life you have a place. Acids have a hydrogen, hydroxide for a base. Acids and bases. In life you have a place. Acids have a hydrogen, hydroxide for a base. Hydroxide for a base. Hydroxide for a base.
Just because. Okay, so let's go through our notes for today. We got a couple of videos that will go with that. All right, so titrations. That's where an acid reacts with a base or base reacts with an acid. If we use Arrhenius, okay, who can tell me what Arrhenius acid and base definition was? Yeah, it's supposed to be 11. This is supposed to be 11. Who can tell me what an Arrhenius acid and base is supposed to be?
Arrhenius acid is supposed to give off
Right.
and Arrhenius base is supposed to accept.
That's Lewis acid. That actually is Bronsted-Lowry.
Oh, just kidding.
So Bronsted-Lowry does a proton, switching the protons. So Arrhenius would be, what was the other definition? We just listened to it over and over again.
OH and H.
OH and H. So an acid gives off an H plus, and an OH, if it gives off an OH, it's a base. So if I use Arrhenius acid and base, then I'm going to get a neutralization reaction where I get water, because H and OH always make water. So I get my water, and I get a salt. And that was hopefully stuck in your head from the video over and over again. Okay. Then we have a base over here. Our base is our OH. And our acid is our HCl. So as we're looking at this, we should be able to identify a base, acid, what's the salt, and what's the water. And we'll talk about salts more towards the end, because not all salts are neutral. What would be neutral on the pH scale? 7. So if I have a strong acid and a strong base, then I will get a neutral salt and water. But if I don't, then I end up with a salt that's slightly acidic or slightly basic, and we'll talk about those later. Okay, so going forward, this is basically a description of how titration goes. You're going to have a measured amount of an unknown concentration placed in a beaker. That is known as the analyte. So when I talk about an analyte, that's your unknown. That's what I'm trying to figure out. Okay? If we were doing more high-tech, we'd use electrodes to figure out the pH of it, but we're not. What we're going to be doing is we're going to be using indicators to tell us when the titration is over. The burette is filled with titration solution of a known concentration. This is known as the titrant. Okay, so the known is a titrant, the unknown is the analyte. But we know how much analyte we put in, and we know the concentration of our titrant. So we're able to add them together until we get to the end, until the point of equivalence. So let's go ahead and go forward here and talk about different things. And I know this goes on to the next page, and then we'll come back to the C. So equivalence point is the point at which all I should put at which neutralization. I can't spell. Occurs, meaning my acid amount equals my base amount, which gives me just water plus salt. Okay? We already talked about the titrant. What was the titrant? Sort of did that up above. This is the one that's my known concentration. And it is what I put in the burette. That's an R, by the way. That didn't come over. Okay, and then we also talked about the analyte up above, and the analyte was what? It was the unknown concentration, but I put a specific amount in the beaker or flask, right? An indicator is a weak acid or base, or weak base, that changes color based on pH. So at a specific pH, it changes color. The endpoint is when using an indicator, the color changes. Okay? Now, I don't care if you write this on the page before or after, but what I'm going to do is go through a couple of different titration curves with you and sort of talk about endpoint versus equivalence point. So the first one I'm going to do is just one quickly that does a strong acid with a strong base. And we're going to start with a strong acid. So strong acid will be close to 0, right, to start off with, or close to 1. So I'm going to start off here. And what happens is over time, I'm adding milliliters of base. Okay, and I'll get this sort of thing going on where I come up like this. And my point right here, does anybody know this point in math, what that's called? It has a specific, I heard what? No. It's called the point of inflection. It's where a graph starts going one direction and starts going another direction. Okay, so that's a point of inflection. That point of inflection is 7, okay, for a strong acid, strong base. So if I've not got a pH meter and I want to find the endpoint close to the equivalence point, then I've got to find an indicator that changes within one pH of my equivalence point. Because I want to be able to find how many milliliters I use to get that. Okay? And if it's within 1, either way, it's still on that man, my brain and my mouth are not talking today. It's still within that steep point of the curve, and they'll be almost exactly alike if it's within 1, either way. Okay? Now, when I get a weak acid versus a strong base, the curve changes a little bit. And I go from starting about 3 or 4 or 5, which is more of a weak acid, and I actually end up here. So now my point of inflection is above 7. So I need to find a pH indicator that changes between, say, 8, around 8, around 9, somewhere like that, so that I can get this number of milliliters of base. Okay? So if I do a weak acid with a strong base, my equivalence point is going to be above 7. That means I want my endpoint to be able to be determined by an indicator that changes above 7. So if we have then, this time, say a strong acid with a weak base, again, here's 14, here's 7, and here's 0. Well, if I have a strong acid, I'm starting down here. If I have a weak base, I'm not going to go as high, right? So my point of inflection this time is below 7. So at this point, I need to pick an indicator that would change at 5, 4, somewhere like that, so that I can get the number of milliliters of base. And then we end up with the last titration curve, which is a weak acid, weak base. And I start here and I go right here. And this one, the point of inflection is probably going to be about 7. But you'll notice there's not very much of a change between the beginning and the end. This is known as, most often, is how we build buffers. Now you have about 3 to 4 buffers in your blood. If you take in, say, if you go to college and you want to get into a fraternity or sorority, this is not, how do I want to put it? This is not smiled upon by the universities, but sometimes they do like an alcohol binge thing to get in. A lot of kids have never had alcohol, and so when they get to college and they start this binge thing to try and get into this fraternity or sorority, they actually get alcohol poisoning, which basically is they've broken the buffers in their system, and if they're not taken to a hospital and have more buffers put in, it actually eats away all their veins and arteries and everything inside and basically kills them quickly. Okay? Because you haven't built up the tolerance, you haven't built your buffers up, so they die. Buffers are meant to keep our pH around the same so that we can function. Okay? All right, so let's watch. There's a video that I want you to watch right now about a titration. It is a little dry, but it tells you what we're going to be doing next time. And it takes you step by step through what each part is and what you're going to be doing. The part that they don't do is they don't show you putting the analyte in, and we'll talk about that when it's done.
The burette, used to precisely dispense a measurable volume of titrant into an analyte solution in a titration, until the endpoint of the reaction is reached. The right hand is used to swirl the flask, while the left hand controls the stopcock from behind the burette. Rotate the stopcock with your thumb, pointer, and middle fingers. This allows better control for delivering partial drops. Check to see if the burette is clean by rinsing with water and noting any beads on the walls. Make sure the stopcock is closed. Bring the burette down below eye level. Use a funnel to add small portions of titrant for rinsing. Wet all areas of the burette with your titrant by rotating horizontally and drain out through the stopcock. Drain all rinses completely. Repeat this 3 times to ensure all contaminants are out. Fill the burette above the 0 mark with your titrant. Pour with the burette below eye level. Pour slowly so the burette does not overflow. Remove the funnel after filling. Check for bubbles in the burette, especially in the tip. Bubbles will cause significant errors in volume. To remove any bubbles, quickly move the stopcock back and forth. Move the burette 0 mark to eye level to avoid parallax, and drain slowly to the 0 mark, or below. Remove any hanging drops from the tip of the burette by touching it to a clean glass surface. Any drops are considered delivered volume. Record the initial volume by using a card with a dark line. This helps darken the meniscus curve for better reading. Read it to 2 decimal places. Add 2 to 3 drops of indicator to your analyte. It is wise to do a rough titration to determine the relative volume needed to reach the endpoint. Place the flask under the burette on a white background. The color change will be more noticeable. Adjust the burette so the tip is inside your flask to avoid loss of titrant. Add the titrant rapidly at first, with constant swirling. As the endpoint approaches, the color will be more persistent. Slow the drops down to 1 per second. Touch the tip to the sides of the flask and wash the sides down with water so that all titrant that has been delivered has reacted. Slowly open the stop clock and allow a partial drop to form. A partial drop just covers the tip of the burette. Touch the tip and rinse until the endpoint is reached. The endpoint is noted by a faint color that is persistent for at least 10 seconds, but not permanent. Obtain a final reading. The volume titrated is the difference between the initial and final reading. The concentration of your analyte can now be calculated. Let's review the steps. Make sure the burette is clean. Rinse 3 times with small portions of titrant. Fill the burette with titrant to above the 0 mark. Remove any bubbles. Drain to 0 or below. Take initial reading. Add indicator to analyte. Titrate quickly at first, then drop per second. Touch tip and wash side to flask. Add partial drops and wash sides until endpoint is reached. Take final reading. Calculate your concentration. Now you are ready to titrate.
Okay, so let's go back to our notes. What they didn't talk about was getting your analyte into your flask or beaker. To do that, we're going to use a pipette. That's what this is known as, is a pipette. And we're going to use either a bulb or, can't think of what it's called right now, a pump. Okay, and the pump has a wheel on this side that you would roll up, and this would come out. And then you can either, as you move it, you can press down on this, or you can press down on this to release the analyte into your flask. Okay. It said we also added indicator into here. Now what happens if I forget the indicator? This is the biggest mistake kids make. Thomas, you staying awake? I know it's hard. This is the biggest mistake that kids make, is not putting the indicator in. And they do the titration, and they use a whole burette of stuff. There's no color. There's no way to tell the ending. It's like running a race and having no finish line. Okay, so you just keep running. It would be like putting something in the oven to bake and forgetting to set the timer. Okay, you realize that you've made a mistake when you smell something burning, right? Okay, so this one you'd realize you'd make a mistake because you drain the whole burette. So we need to make sure we add an indicator, because an indicator tells us when the finish is, when we stop. Okay, let's look at the calculations. Now up here I've got M1 V1 equals M2 V2. You could also say MA VA equals MB VB, just saying base and acid. Okay, Thomas, you following us now? We're on the notes. Okay. All right, so you also remember from the video at the very first, it said that you also need to times it by the number of hydrogens that you have and hydroxides. So if they're both equal to each other, 1 and 1, I can sort of ignore that. Okay, so on this first one, this one is not in your notes, but you can add it to you if you'd like to. We'll do the next one after. This one is in your notes in blue. But I wanted to do one that was simple, where you didn't have to deal with the hydrogens. So as I'm going through, this one is my molarity of my base, actually. And this is, let's see, if needs, molar needs to titrate. So this is my volume of my base, and this is my volume of my acid. And so I'm looking for my concentration of my acid. Okay? So as I'm going through, I just plug it in. So MA, I don't have. VA is 10.00 milliliters. MB is 3.4 molar. And VB is 35.4 milliliters. Okay, solving by math, I just divide both sides by 10 milliliters. It cancels it out over here. Over here, the milliliters cancel, and I'm left with molarity. So I take 3.4 times 35.4 divided by 10. Somebody crunch that number for me. Okay, 12.036. So we had two significant figures, so that'd be 12. Do I have a second on that? Yep. Okay, so that's molarity, and I would put HCl to finish the units, and I'd be done. Okay? So what happens if we do this, the one in blue, which is the one that you've got in your note packet, is as I'm going through, I'm going to identify the things that I have. So what is the molarity? I'm looking for the molarity of H2SO4. What one's that? Acid or base? Molarity of the acid. So I'm looking for that. I don't know what that is. But I've got that I used this volume of this. So this is my volume of my base. And this is my molarity of my base, because those two are tied together. And I put in how much of the acid to start with. Well, that's right here. So that's my volume of my acid. Now, the thing that I notice really quickly is that I have two H's on here, and I only have one OH here. So I'm going to need to times the OH by 2 so that the H's and the OH's cancel out. Okay? So when I do my MAVA equals MBVB, on the base side, I'm going to times that by 2. Now, I could have written the equation like they did right here and balanced it, and I could see real quickly for every one of these, I need 2 of these. But I can also do that by just looking at it in the problem and not having to write the equation. Okay? So plugging in, my MA, I don't know, so I just write MA again. My VA was 25.9 milliliters. My MB, 0.32 molar, times my VB, 43.35 milliliters. Again, I want to get all the numbers on the one side, so I'm going to divide by 25.9 milliliters. That will cancel that out on this side, and it will cancel the milliliters out on this side. So then I can quickly plug that in my calculator and get the answer, which is what? It looks like we have two significant figures with molarity. And then divide. Yep. Order of operations in math. Okay, we got an answer. Point 5455, which one? 54, capital M. And what were we trying to find the molarity of? How do I finish labeling it? Good. H2SO4, and that would be my answer. Okay, so this is a pretty easy equation, right? Yes. We did. I forgot the 2. Thank you. We do need to times it by 2, so it's going to be twice as much. So thank you for that. No, that's good, because we would hate to have that wrong in our notes. So we needed to times that by 2. It's 107 or 108? 107, so 1.1, because we had 2 sig figs. 1.1 for 2,6-fix. Thank you for catching that. Yeah, we need to remember, I forgot that. We need to remember that too and make sure we bring it down. Thanks for keeping me on my toes. Here we go, next one. Okay, so remember I told you we were going to talk about salts later. So if a salt added to water makes a hydroxide, we've got a what? What were hydroxides? They're bases. So how do I know here? These ones right here, if I have what's called a metal oxide, where are my metals? On the left-hand side of the periodic table. What was on the left-hand side of the periodic table? The tetras pattern, where we learned our 6 strong bases, right? So if I know it's on the left-hand side, it's going to be a base. Okay, if it goes to hydroxide. So also thinking that same kind of thing, if I know it's a non-metal oxide, where are non-metals found? On the right-hand side of the periodic table, what would you find on the right-hand side? What are these? They're acids. Now, we might end up with strong, we might end up with weak, but we'll end up with something, right? Okay, I've got one more video to show you real quick. This one you've probably heard of before or seen a little bit of before, but we're going to take it from a chemistry point of view. I'm going to skip forward a little.
Different ways, the burning of fossil fuels can cause our rain to become acidified. Sulfuric acid arises from the burning of coal and oil, mainly in power stations, whereas nitric acid arises from the exhaust pipes of our motor vehicles. You will also see some of the effects acid rain has on our environment. Firstly, it's important to understand that rain is naturally slightly acidic. Whilst falling to the ground, the rain dissolves carbon dioxide from the atmosphere to form carbonic acid, a weak acid giving natural rain a pH of 6. It's when we burn fossil fuels that much stronger acids get into our rain to form acid rain with a pH as low as 3. When the pH changes from 6 to 3, what do you think the acidity increases
an answer.
by?
Hold up with your finger.
2
what
times,
do you think it is?
3 times, 10 times, 1,000 times?
So 1, 2,
Pause
3, or
and think.
4. Choice. 3. I think. I heard 3, I heard 4.
Remember that each
Okay,
change of 1 in pH is a 10-fold change in acidity. So changing from 6 to 3 is 10 times 10 times 10, or 1,000 times more acidic.
So it's a lot more acidic.
We'll consider sulfuric acid first. Plants need a little sulfur to grow. They obtain it from sulfates, for example potassium sulfate, found naturally in the soil. The sulfates are taken up by the plant's roots, and sulfur atoms become bonded to carbon atoms in the leaves' proteins. When plants die and eventually form coal and oil over millions of years, these sulfur atoms remain bonded to the carbon atoms. The sulfur content of coal and oil is usually between 1 and 4% by weight. What do you think is produced when fossil fuels containing sulfur are burnt?
Okay,
Pause the video whilst you think.
Combustion reaction, what's formed?
When the coal is burnt, the sulfur and the carbon atoms join with oxygen from the air and are released into the atmosphere as carbon dioxide and sulfur dioxide.
SO2.
In the presence of sunlight, a photochemical reaction will take place where sulfur dioxide reacts with more oxygen to form sulfur trioxide. This dissolves in the rainwater, forming sulfuric acid. Let's now consider how nitric acid gets into the rain. In the high temperature conditions in the cylinders of our motor vehicles, a small amount of nitrogen and oxygen from the air can react. Remember that air taken in to combust the fuel is nearly 80% nitrogen. So exhaust gases from vehicles contain small but significant amounts of nitrogen oxides. Once the oxides of nitrogen are in the air, they react with more oxygen, just like we saw with sulfur dioxide, and dissolve in the rainwater to form nitric acid. If the rain falls on limestone soils which are alkaline, the acidity may be neutralized. However, if the rain lands on neutral or acid soils or on vegetation, then it can cause damage. So why is this acidity harmful to living things? Well, living things don't grow well in acid conditions, and it's easy to demonstrate this. Soak a slice of bread in vinegar and another in pure water, leave them open for a little while, and then leave them covered for a week. You will find that the bread soaked in vinegar has not gone moldy, whereas the other bread has. In fact, we use vinegar to preserve food in a process called pickling. This is the case because certain enzymes which are vital for growth are unable to function in acid conditions. The other main problem is in the soil. Whilst naturally occurring toxic metals such as aluminium are insoluble and therefore fairly harmless in neutral soil, they become soluble in acidic soil. They then get taken up by living things and take the place of essential metals such as zinc and iron. To add to this, the hydrogen ions in the acid rain will replace essential metal ions such as potassium, magnesium and calcium, which are normally held in the clay soil, causing these essential metals to be washed deep into the subsoil away from the roots of plants. So to summarize, normal rain is slightly acidic due to the dissolved carbon dioxide, but acid rain contains sulfuric and nitric acid, making the rain 1,000 times more acidic and dangerous for many living things. Sulfuric acid arises from the burning of fossil fuels containing sulfur. Nitric acid arises from the combustion of atmospheric oxygen and nitrogen in the high temperature conditions in the cylinders of petrol and diesel engines.
Okay, so that goes a little bit deeper than I think that you've had acid rain before when you talked about it in elementary school or junior high. You need to remember that. That's going to be part of your SAGE test, and you need to know where they come from. So tell me what comes from combustion of fossil fuels.
Oh, CO2 and SO2, which
Okay.
is
Is sulfur dioxide that then reacts with more oxygen in the atmosphere to make sulfur trioxide, which then mixes with water, and then you get sulfuric acid. Okay, what about the combustion engine? What comes out of that one? Like your cars. The nitrogen and oxygen. So nitrogen monoxide reacts with more oxygen in the atmosphere, making nitrogen trioxide, which then mixes with water and makes nitric acid. Okay? Yes?
Are we going to have to know all the stuff that it mixes in with to make the end result?
As long as you know where they come from and what is initially given off, you'll be okay. Okay? The other thing that they gave you that's a little tidbit that is something that you probably ought to remember is, what did they say air was made up mostly of? 80% nitrogen. Okay? So our bodies use oxygen, right? So we have to breathe a lot of air to get the oxygen that we need out of the air, because most of what we're breathing is nitrogen. Okay? Thomas, you got to stay awake for me, bud. Okay, so this is what we're going to do today. We're going to break into our groups. I'm going to have you four work together. You four and you four. Okay? We're going to do the strong acid, strong base, actually it says strong or weak acid is what it actually is, POGL. And then do the pre-lab, get it stamped, then start working on assignment 3. You need to make sure you turn in your blue POGL from last time. We'll correct 1 through 3 next time before we go into lab, or I might even push it back one more time. Okay? If you're having problems with the assignments, make sure you're coming in and getting help, though. All right? Okay, let's move. Let's go. Got till 40 or 22. 40 minutes after.